This is Minglan Yu from Harvard University. Welcome to this P4 workshop talk. It's presented by Rong, who's an Intel fellow, and Reshma Sudarshan, who is Director of Applications Engineering Intel. And they're going to talk to us about how to support NDP with Sonic. Yeah. Rong, please start.
Thank you, Milan, for the introduction. Hi, I'm Rong. Today we will present, me and Reshma will present to you NDP with Sonic pings, low latency, high performance data center transfer into Sonic. It is a joint work with the original NDP team by Mark and Austin, and with Intel's team. We want to show how the NDPs can be implemented in Sonic pings. So, as we all know, TCP has served the internet well for the past 30 years. However, it fails to meet the stringent performance requirement of high performance and low latency in the data centers. So there are many attempts of offloading the traditionally software-based networking stacks into hardware using technologies such as RDMA. However, these hardware accelerated technologies makes the network even more vulnerable for congestion and packet losses. That's why we have seen a lot of the new innovations in the space try to come up with a new congestion control algorithm or transport algorithms that can deliver the high throughput and low latency in the data center environment. And NDP is one of such algorithm that was proposed in 2017 by the team led by Mark Handley and Austin and their team. And Mark presented the NDP and they won the best paper award in that year. And Intel has been working with NDP team in trying to bring it into Sonic. So I will give a brief introduction to the NDP, and then Reshma will talk about how it can be implemented into Sonics. So right off the bat, the NDP goals is to deliver low latency. They specified as latency. So it's really the ultimate goal is provide low latency performance for data center transport and to provide a predictable request and response behavior. And it does by using zero RTT setup. So there's no a setup phase required like a TCP. And all the flows are just do fast startup, setting at a line rate. It only keep a very short switch buffer queue, and then allow incast behavior to be gracefully degraded. And the receiver can do prioritization, so allow a flow that have different treatment. So a flow with more important can be delivered first. Their packet can be delivered first. And it also enables predictable high throughput because they adopt packet load balancing, per packet load balancing to the multipath that is available to the NDP senders. So in a nutshell, what NDP does is just start, spray, trim, and pull. At the sender, there's no need for prior handshake, so there's a zero RTT setup. And the sender will just send the first RTT of data at line rate. And it does utilize the multipassing, so it does per packet spraying. And if packet lost and receive the notification from the receiver, it will does fast retransmission. What network switches does is under congestion, it will just do packet trimming, and then they only cut the payload, and the header will be forwarded to the receiver, and such a cut payload packet will be treated at a higher priority so they can reach the receiver faster. And at a receiver, after the first round trip time, the receiver just pulls the packet at its own queue. So if a particular link is congested, so they will pull at a slower speed. And the sender will only send after the first round trip time, and the sender will only send packet when they receive a pull packet. And the prioritization is implemented at the receiver so they can choose which senders to pull first. During the NDP talk, they had a very nice video, so I'll share here. This is what the behavior is at network switches. If the buffer at the network switches becomes full, the payload will be cut. And as you can see, the thin headers of those cut packet will be sent to the priority queue, and then they will be sent out to the wire ahead of the real packet. And at the receiver, once those packet comes back after the first round trip time, and those pull packet will be issued. So for whenever there's a packet arrive, there will be a pull packet that will be issued to the sender. And that is how the receiver-driven NDP can control the sending rate of the NDP senders, because those power packets are sent at the rate that we want the incoming packet to arrive, except the first round trip time. So as you can see now, the pull packet is not free flowing going out. It is being sent out at the desired rate to the sender. So now it's very well, nicely controlled by the receiver. And at the sender, it will only kick out the packet after the first round trip time. It will only pull out the packet when there is pull packet comes. That's how they send the packet out. This pull packet will trigger either the retransmission of the original lost data or new data. But all the data packet will be controlled by these pull packet that coming into the sender. The NDP can achieve very high low latency by cutting the payload at the switches. They actually make the queuing delay very low, so the overall end-to-end RTT will be very close to the base RTT. So so they can enable faster flow completion time. This is a workload that they run with compare the flow completion time for 90K byte flows with some random background load in a 432 node fat tree. And in this experiment, NDP and the MPTCP can achieve 80% utilization, and DCTCP, DCQC achieve 75%, while achieving the high throughput and the flow completion time, as in the graph here, as you can see, NDP delivers much faster flow completion time compared with the competing schemes such as DCTCP, DCQC, and MPTCP. And then I will switch to Reshma. She will talk about the NDPs in Sonic and how we take this, the great algorithm, and then implement into our Intel products. Off to you, Reshma.
Thank you, Rong. With this background of how NDP manages the incast in case of congestion to achieve overall reliable end-to-end congestion control, and map that to what it translates to in real hardware metering for each egress port and each of the ingress pipes. During incast, the items that we need to look for would be if the egress port is overloaded, how do we ensure the good put to the capacity of the egress port? How do we handle transient bursts using deflect on drop buffers? And how do we ensure the overloaded state of the egress port is has a feedback loop to the ingress pipes so that we can recirculate the packets and with the marking that we can handle in the second pass to basically drop the payload and prioritize the headers back to the destination via a high priority queue. So to implement this NDP items that we just described in Sonic, we definitely required addition of new tables in the PSI pipeline. The new hardware tables could not be manipulated by regular Sonic as is. So we implemented NDP in proprietary methods to program the P4 pipeline using proprietary barefoot runtime BFRT interface. As you can see, we definitely needed to transition into standard methods to configure these tables. Next slide, please. I also want to mention Dragos and Georgios who actually worked on that. Now coming to pins, which is my primary area of focus for this presentation, was actually introduced by Michael in a keynote in the same P4 workshop. It stands for P4 Integrated Networking Stack. It's a co-development project between Intel and Google, and started off as a standards-based open approach to SDN on Sonic switches, adding SDN capability to allow remoting PSI objects in a programmable switch. So using a standard modern P4 runtime interface as the common uniform abstraction, it enables essentially two sets of features: SDN managed PSI tables and non-PSI extension tables. The extension of non-PSI tables is something that helps users with pathfinding, feature velocity in terms of implementing protocols like NDP. And sometimes users just have proprietary IP in their applications that they want to write in a secure environment of Sonic and pins, and have this uniform management interface across applications in their network. So making PSI changes requires changes in all levels of stack, whether it is in ASIC or SDK or PSI itself or Arc Agent and the applications. And this PSI P4 extension API is generic enough to provide CRUD support to any new tables that user wants to add. The use case is that a programmable device can be programmed using pins, P4 extensions, till P4 mechanism to control the underlying device's desired, and the PSI functions are not yet completed for this use case. And within Intel, pins is a common management interface that we are looking for in across all the devices, host, NIC, and switch. And the design is field upgradable and extensible. Using set forwarding pipeline, we are able to push new P4 programs in a running P4 programmable switch. In this slide, what we see is the current PSI pipeline. When we assume this underlying PSI pipeline as the baseline, and we want to basically create extension tables to as touch points to extend PSI features. To add a couple of extension tables in a couple of places for a given use case in the pipeline, and they are programmed in a manner that is basically independent of the data path. They would change the metadata that is used by the pipeline, or they would create a new metadata, which is not used by the pipeline's regular flow, as we will see in the subsequent slides for how we manage with NDP. Next slide, please. So as we discussed earlier, we require to keep track of per port meter for NDP packets. And in the egress stage, where this extension table needs to be added, we are going to be able to monitor the egress port capacities and the state, how it is overloaded. And we add these tables and change the metadata to basically mark the packets as required to be trimmed to provide that feedback loop back to the ingress. And also change the priority queue so that the trimmed headers are sent in a higher priority queue along with the control packets as compared to low priority queue. Next slide, please. Now this is the second pass where and after the regular layer 3 routing and forwarding phase, when we look up the egress port, we are able to, at this time, introduce the metering logic until the egress port is no longer overloaded. And that's a heuristic value that we have come up with to be able to handle that. So at this point, the metering is enabled, as well as once the flag is set for this particular packet, we are able to trim the payload and send them to high priority queue as well. This ensures the feedback loop also externally overall from the NDP perspective back to the destination, so the overall protocol can take effect from that point to inform the sender and draw the traffic at that point. Next slide, please. As another example, other than NDP, to see how PINs actually works, this is a broadband network gateway example. And here the subscriber ID needs to be mapped with the incoming traffic, and we classify that basically using double tag. And this functionality of decapsulating double tag packets is not there today in PSI Pipeline. So which makes BNG a good candidate to use basically pins. That's the first red box here, which is the extension table that's been added to achieve BNG use case. And also the rightmost red box here to catch anomalies within the network. If there is a DOS attack, we can basically introduce that dynamically within the switch and handle that traffic beforehand until it becomes a grave problem in the network downstream where compute resources would be needed to be used for handling that, making that much more expensive. So also the user to be able to add new proprietary logic for anti-spoofing algorithms to be able to achieve this as well. The other use cases that are there today also assume basically the underlying PSI pipeline as the baseline and be able to add a few items to extend the pipeline to achieve the overall use case that they require. BNG, Broadband Network Gateway, we just saw that. 5G, as I mentioned, PINs is applicable to any programmable device, including SmartNIC. And in case of 5G, we have seen use cases where the far edge is able to add 5G accelerator functions using PINs on one side, whereas use the local control plane with BGP, VPN, VXLAN to connect to the rest of the network all the way back to the core. So another such example is OVN, where there is a requirement of underlay and overlay, and we could view this as the dual brain scenario where pins can be used to basically identify the metadata in the Geneve headers and look up something new like a virtual port that's also there in the Geneve headers, and basically a good candidate to use pins as well. And there are other use cases that have been used before, RTP or multicast, server load balancer, and custom telemetry collections solutions as well that are able to use pins to achieve what they need. Next slide, please. So overall, the advantages of the P4 integrated network stack is that we now allow SDN controllers to participate in the SONiC ecosystem, and we have the standard way to control a running P4 forwarding switch using P4 runtime API. And P4 runtime API itself is standard, open, and modern way of managing P4 forwarding planes, and is applicable to all the ASICs that have varied levels of programmability. Pins allows sharing of objects between SONiC and controller applications. This is something that is of major advantage. We can definitely have separation in layer 2, layer 3 using multiple methods that exist today, like VRF and layer 2 separation as well. But what pins allows is that the objects are being shared. In case of OVN, if we have a special lookup that is needed, and we can reuse, suppose, a tunnel interface to tunnel the packet back out to the rest of the network, and for which the tunnel object can be reused by the one that's programmed by local control plane. Again, work inside compliant environment and have standard framework to extend pipeline to various proprietary applications. We really look forward for wide adoption from the community. We're adding more to it, and we will come back with the information that we're adding to pins in the near future. Thank you.
Great, thank you. Thank you for the nice talk. The introduction of pins and applying to NDP to a real hardware is really exciting. So I want to start a question about NTP because I know in Intel Barefoot platform, there have been other congestion control protocols developed like HPCC, like that directly use INT signals for congestion control. There's also a new version that allows switches to directly send information back to the sender so that we can get sub-RTT feedbacks. Together, NDP is also a really nice protocol. So I wonder from practical point of view, these protocols have different levels of accuracy and different levels of difficulty in implementation. I wonder from practical point of view, what's your view among these protocols? Would one of them be better than others, or is there some guidelines for like researchers in academia to decide what kind of next exciting congestion control protocol we should develop?
Oh, that's a great question. I guess it is a hard question for Intel to answer. Mm-hmm. We love HPCC, and we also like NDP. Actually, these are the two algorithms that we are really looking into implementing in hardware, as you mentioned. If the switch can provide INT information, and then I think is a lot more richer information. So I think the end host can take advantage of that, in my opinion. And for the benefit of NDP is that you just drop the payload. The switch design may be simpler, I think, but the receiver, the NIC, they're more involved from the NIC. You have to construct the pool queues, deliver the packet. But we believe those are workable. Maybe NDP from the hardware point of view, NDP is a little bit harder. But from Intel's point of view, it's really up to the CSPs. They're the user of these algorithms, and we just provide the hardware acceleration to, as much as possible. And we give them the choices of choosing different algorithms and to suit their particular environment and their particular need.
Thank you. Yeah, it's a really good point that Intel aims at supporting a diverse set of protocols. So now I want to get a bit more into the actual implementation of the NDP on pins. So I see that in order to support NDP, we do this recirculation back to the ingress point. I know this is a good workaround that make it possible on today's switches. If you were gonna add new features in future generations of switches, would there be any variations you would add that would make the NDP implementation easier? First, do you see recirculation as a problem causing more maybe delays and reordering at the NIC, or yeah, do you see that a problem, and do you see in the future certain switch features could make it better?
Great question. Rong, I will take the first pass and then you can add to this. Recirculation is required once we already exhaust the option of the transient bursts that we handle using the deflect on drop buffer. So that is there. We have multiple, I guess, levels of handling the overload. Yes, I think we have another new protocol that we are actually working on. One thing I want to mention is that the recirculation itself doesn't really cost much in terms of latency, but I hear what you're saying, and we definitely have multiple ways of handling this, and the last resort is using the recirculation, and we have another protocol that's actually coming up. Rong, do you want to add to it?
No, that's good. Yeah, thank you. You answered well.
Thank you. So I see that pins have been able to support a wide range of use cases beyond NDP, and it's a really nice way to integrate P4 into Sonic. So I just wonder, once people write programs in pins, it will later be compiled down into different types of platforms, not only switches, but also NICs. I wonder if you see, from your experiences, do you see any difficulties or challenges in terms of compiling down to different platforms?
That's a great question as well. The user-facing P4 program with this SDN capability that PINS adds is able to compile and pass that P4 artifacts to the P4 runtime server that's running on the switch, in this case, either switch or SmartNIC in the near future. We have containers within the Sonic ecosystem that actually translate these artifacts and map them to corresponding ASIC-DB entries. So that automation is sort of built in when we added pins. But yes, what you're saying is absolutely true, that the different targets, such as SmartNIC, as programmable and extensible as they are at the moment, they may have variable types of the pipelines, and some amount of mapping would be different in those hardware targets.
Do you have examples of why it's challenging? Because I could imagine maybe some NICs doesn't support certain features that you will have to rely on maybe the switch CPU to handle things that get slower. So it's like both a feature set problem and a performance problem. Yeah, I just wonder.
I see.
If you see specific problem, and how do you handle those?
Got it. In a NIC, the pipeline itself is not as extensive as it is on the switch. So if we see that the pipeline is cut in half, increase the number of buffers to suppose 2x, then the mapping becomes a little, different, basically. The best part of pins is that we should be able to use the local control plane as well, other than the remote control plane, writing and extending the features that are available. So there are multiple ways we can control the number of features that are enabled, with that the number of tables that are enabled within each target. If we do purely remote control plane, then we have full access to the entire pipeline in terms of what tables we can add. And now the smart NICs, which are almost similar to a regular switch, we program the required tables based on the features that are specific to the use case at the edge on the smart NIC with the host. And we have that leeway to do that using pins.
Great, thank you for the detailed explanation. That's all for us, and thank you for the great talk and answers. Michelle?